Welcome to the Bug Bash podcast, where we talk about all things software correctness and reliability. I'm your host, David Wynn. The map is not the territory, but without a map, we're completely lost. So what happens when that territory is vast, ever-changing, and worse, is about distributed systems? In this episode, I sit down with Kyle Kingsbury, the renowned researcher behind Jepsen, to discuss a monumental effort to chart one portion of this landscape, the Distributed Systems Reliability Glossary. Kyle explains why he, in collaboration with Antithesis, felt the need to put this all in one place, creating a practical roadmap for testers and engineers navigating the field. We explore the challenges of creating directionally correct definitions, yelling at hard drives to make more errors, and why even the most rigorous formal models drift apart from the code they're meant to describe. For a deep dive into subtle bugs that defy simple explanations, the future of reliability in the age of AI-generated code, and the white whale that Kyle's still chasing in his own work. Stay tuned. Kyle, thank you so much for being on the show today.
Thank you for having me. It's good to see you, David.
So for those who don't know you, do you want to take a moment to introduce yourself and talk a little bit about who you are and what you do?
Sure. I am a distributed systems researcher. I sit kind of between industry and academia, and my goal is to verify real distributed systems and try and find out whether or not they do what they claim on the jar. And to do that, I'm bringing in ideas from the literature on distributed systems consistency and availability, and trying to leverage some of the testing techniques that others have built to make our systems better.
Absolutely. And you do a lot of your work in public. I think a lot of people have seen your talks. They've seen your lovely artwork, all drawn by you, right?
Yeah, I do all the slides by hand.
Mm-hmm. I think that's a great thing to see. It really helps stand out, obviously, in a world of AI-generated stuff and things going on. It's nice to have a very, very direct connection to the creation of what's going on here, right?
I think so. I also think that it helps with information density because it's easy to put too much on a slide. And if you draw things by hand, you're limited in how much detail you can pack into one image.
Yes. Or sometimes you're limited by your own handwriting, because I tried it the other day and whoo, I couldn't read what I'd written. And so I think I'm going to have to go back to
mine's
Yeah, I'm going to have to go back to school. This is not good. That brings us to what we are talking about here today, which is the Distributed Systems Reliability Glossary that is being published. Tell us, so first of all, what is it?
So this is a glossary, a giant map of terms to short explanations of distributed systems concepts that we think will be useful in testing of the distributed systems. So things like different terms of availability or different consistency models, different kinds of faults that might occur in systems. And our goal here is to provide some kind of, not standardized, but at least indicative terms that you can use to talk about these things with your colleagues. And maybe also a roadmap for testers when they're trying to think about how to build more reliable systems.
What brought it into creation? What was the moment where you sat down and were like, okay, we need to put this all in one place for one reason or another?
You know, I've been trying to do a little bit of this work on Jepsen's website for a while. There's this clickable map of any sort of database consistency model. And also in the last year, I've started writing explanations of certain database phenomena in depth. That work is ongoing. I'm sort of publishing and editing it incrementally. But neither of these tackles, I think, the totality of what you want to know as a systems tester. And I was talking with a wonderful colleague, TW, over at Antithesis, who said, hey, we don't think that there's a resource for this. No single blog or article or book really seems to integrate these ideas, the sorts of ideas that I work with every day in my work. And he asked if I might be interested in putting together a text. So from our discussions back and forth, that kind of seeded the idea of what this glossary could be, who it's for, and how I wanted to shape the voice of it.
Gotcha. So why hasn't this been done until now? You mentioned it comes from a lot of different places, both on the academic front, on the industrial practice front. What makes all of this together? Is it just a tall order to be like, could you just sum up distributed systems for me and write it down real quick?
Yeah, I'll get right on that.
Yeah.
It's funny because I also don't think that I'm the best person to write this because the field of distributed systems is so vast and so complicated, and every time I go into a paper, it's like, my goodness, you devoted years of your life to exploring this little corner of it, and you built this incredible idea, and I get the vaguest shape of it. But I personally am lucky enough to have worked at the intersection of a few different fields. I come from a physics background educationally, so I bring a little bit of like contemporary experimental physics ideas and some things from psychology and in terms of experiment design. I can write acceptably. I've been an engineer building distributed systems and building on top of them. I've worked frontline support, so I know kind of what users feel, and I've done mobile development as well. So from those, I get this kind of synesthetic view of distributed systems. I think fundamentally they're interdisciplinary systems, and so if you want to do something that really summarizes them, you need to be drawing from those different fields that haven't necessarily collaborated or been unified as frequently as one might like.
That makes it sound like we're approaching this glossary from a very practical perspective, just because the more formalized we get, it seems the more specialized we get. And so we could have written the same glossary on Paxos alone and all of the different elements that go inside of it, right? But instead, this represents a move towards a practical practitioner's perspective, right? If I have a system that's been dropped into my lap, that's never happened before, that I totally wrote and designed from the ground up, and I kind of need to wrap my head around it and describe it in ways that I can translate, this would be a good reference to help use some common language and bring that together in. Is that the right idea?
Yeah, and to give you a jumping off point when you're thinking about what kinds of properties am I looking to test for, what kinds of phenomena might be bad, what sorts of faults might I want to inject. And by having a summary of those things, giving you something you can kind of skim through and check off, like, oh, I knew about this kind of disk fault, but not that one. Maybe I should dig into that. We're trying to give people a map of the territory. Obviously, every map is wrong, and this one is especially so because in distributed systems, people use the same words for different things. Like high availability, depending on who you talk to, can mean every single node responds all the time, or only a majority of nodes, or maybe just one node, depending on the hour. and so any definitions we give are going to be incorrect in some contexts, but hopefully they are directionally correct in the sense of giving you an idea of where to look next and how to fit ideas together.
Right. If I'm reading correctly here, the goal is to give univalent, directionally correct definitions, which, one, I knew what it meant. Don't worry, you don't have to explain. But for the people behind me in the room that you can't see, that meant what exactly?
Well, and now that I'm hearing this, did I come up that? Was that TW?
Feel free to put the blame wherever you want, but then you got to explain to me what it means.
Yeah, so instead of trying to provide an exhaustive definition for every single concept, we're aiming to give simple, approachable definitions that are good enough to get things done. We're not going to go into all the subtleties of the ways that transaction dependency edges can be connected. But hopefully the intuitive sketch we give will give you a feel for why it's important. And then if you care, you can go and dig into the literature and, read all 150 pages of Adya's thesis or whatever.
There are a lot of links. Many of the words are blue in a good way.
Yeah, that's a really important thing, actually. There are many papers that I've come to time and time again, and here I have to give credit to my friends and colleagues, people like Peter Bayless and Peter Alvaro, both Peters, people like Katie McCaffrey. These folks have brought me different papers over the years that have become sort of seed crystals for growing my understanding of systems. And so I wanted to give people this kind of condensed reading list. A lot of these are woven throughout Jepsen's existing documentation or the written reports I've written, but I really like that we were able to bring things together into this more concise document.
Would you say there were any terms that you sought to define that perhaps the discussion around them is particularly heated? You brought up availability and high availability. Are there any others where we put a little bit of a stake in the ground for the sake of practical clarity as opposed to wading into what I assume is the distributed systems equivalent of Vim versus Emacs and so on and so forth?
Yeah, there's a bunch of places in here where like in search of clarity in this context, TWRI like staked down a particular term. For example, like disk versus storage fault. In one context, you'll see it called a disk fault, in another, the storage fault. If you're interested in different sorts of storage systems, for example, like a flash system or like a persistent DRAM of some kind, maybe that's not really a disk, but it's still subject to similar sorts of faults. What is bit rot really? Well, we have an intuitive idea, but it's surprisingly hard to really write down because there's this qualitative feel. Like bit rot is something that happens slowly. It's the vegetables in my ADHD fridge, if TikTok is accurate, which are slowly going bad and being ignored.
Yeah, it's definitely the air I have not blown into my desktop tower over a while, and whatever comes out when I finally blow it. Yeah.
Oh yeah, that's bit rot. Actually, when the bits flip, they emit a little bit of dust, and if that leaves the seal, it
Or it's the other
builds
way
up.
around. I'm not sure if the dust gets in there and flits the bips. I don't know.
Yeah, one of the fun things about this was like there's a lot of like urban legend or apocrypha in distributed systems, which um, I I really struggled with how much of it to include. We know, for example, that if you yell at hard drives, that their error rate will go up or their latency will increase. There's like this fantastic video of someone in a data center going ah, and like watching the graph rise.
Wait, what? This is the first I've heard of this. Is
I
that
know.
true?
Another one is like cosmic rays. They do occasionally flip bits, and Google has that famous paper on like somewhere about how important ECC was to their infrastructure. But finding like objective, peer-reviewed, or like just core papers or web pages to cite was really difficult. I know because I've talked to people who experienced it that like occasionally a node clock can jump like 30 years into the future. And when that happens, NTP like thinks the error is too large and won't correct it, so you can have a node sit there for a while. This is just like a hardware fault that occasionally happens. Do I have like a proper citation for it? No.
Yeah.
And so I try to draw this balance between, like referencing the Apocrypha, but trying to pin down as many sources as I can in the work.
Yeah, I like that your sources are very professional because my best reference for cosmic rays is the Mario 64 speedrunner who managed to make a jump, and mid-jump, there was a cosmic ray that flipped a bit that caused the jump to go through a floor and break a segment for a world record that he's never been able to recreate or repeat. And basically due to an exhaustive search of the help of the internet and the speedrunning community, which for those who aren't familiar with the speedrunning community, it's quite an in-depth community. They have determined this must not be anything that they can reliably reproduce, and it must have been a cosmic ray. So I just think of Mario jumping too high, higher than he should.
I mean, I would believe it, or thermal noise, or like leakage from a nearby bit. There's different things that can cause machines to have these memory errors, and it's not within most of our threat models, so to speak. But I do want to highlight it in this work.
Do you think that because a lot of these things, I think, were more familiar to developers and practitioners when we were in control of more physical systems, right? That's part of why the language is a bit more physical, right? But now with cloud becoming so common and that being more or less pushed into just sort of CLI land, and I could imagine that there are machines next to each other, but I'm not thinking very hard about it anymore, sometimes to great benefit in the sense that there might be updates they could roll out behind the scenes to the hosts that I don't have to pay attention to, and that's great. But on the other hand, it also takes us one layer removed from some of these considerations. Do you think that there's like a blind spot that might be emerging in recent development trends because of that?
It's a really interesting question. To roll with your physical metaphor, we have this concept in storage systems of like a lost write, and it's very clear what that means. You intended to put some data onto the hard disk, and somewhere in between, in the page cache or the I/O queue, or maybe in a little bit of memory that sits in front of the disk inside the disk hardware itself, something forgot about it and it never made its way onto the disk. And there's a single objective source of truth, like the bits physically on that platter or in that storage device. You could define that clearly. And naturally, there's an analog in any distributed storage system or cloud system. Like a lost write on EBS should exist. It would happen if you tried to write something and an EBS said yes, and then it wasn't there later. But what does it mean for it not to be there? Formally, in a cloud system or in any sort of asynchronous network system, uh, it could just be that the system delays visibility of your write, and so every read you perform never returns it. That would be indistinguishable from a lost write, but is it actually lost or is it just stale? Those are two different safety properties. So what do you what do you do there? I don't know. This is not a direct answer to your question, but it's something I think about a lot.
Yeah, because well, and that brings about the need for the glossary, right? Because being able to talk about some of these terms clearly is a meaningful improvement towards getting to where we need to go, right? And I have to assume, because the glossary takes up finite space, and as far as I know, the error space in distributed systems is infinite, that something probably was left on the cutting room floor. Maybe was there anything that you decided to leave out of the glossary this time because, oh, that's too esoteric. Oh, that's no, probably not too esoteric. But whatever qualifications that you thought left something on the cutting room floor.
Yeah, when TW and I were talking about this project initially, we had this idea that it would cover testing techniques as well. And so I wrote a whole bunch of sketches of ideas like climbing the lattice. If you have a data type which has a semi-lattice structure, that is to say, you can join any two elements and get something that merges them together, like a set that always grows or a number that always approaches a maximum, CRDTs, for example. You can exploit properties of that lattice to write a test. You can show whether or not any given read is causally reflective of some previous write. If it's in the sort of lattice tree that could have possibly contributed to it, you know it's there.
Mm-hmm.
And that's this idea that I don't think I've ever seen written down. Someone somewhere must have done this,
Mm-hmm.
but I don't know the citation yet. We would love to do a compendium or some sort of series about these testing techniques, but we didn't figure out a way to bring it concisely within the scope of the glossary.
Well, of what did made it, the phenomena section has a lot of phenomenon in there. And I definitely know which of those is plural, so disregard my pronunciation.
do, 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 do.
Exactly. Do you have a favorite phenomenon that you guys listed in here?
Oh. Okay, my favorite, and this is not a real one in the sense of that it's not in the literature as far as I know, but it's G nonadjacent.
What is G nonadjacent?
This is a term which I have made up and I am shoving into the glossary in hopes that it will get adopted. It is a totally non-intuitive but mathematically rigorous phenomenon, which is maybe the worst kind because I want to give people intuition for things. It's hard to reason about why this is bad. But G nonadjacent is precisely the phenomenon that snapshot isolation forbids.
Okay.
And it's characterized.
Let's expand that a bit. Yeah.
Yeah. So G nonadjacent refers to a cycle of dependencies between transactions, such that the transactions can be linked by any number of write-read or write-write dependencies. That is to say, somebody observes another person's effects, or they overwrite that person's effects, that transaction's effects. And there can also be some number of read-write dependencies, which is to say, somebody observed a value and then someone else overwrote it. And when you alter the value someone else read and set the next value in the sequence of values, your transaction should happen later in a serializable system. In a snapshot isolated system, the cycles of transactions which are permitted are exactly those which have no two... Sorry. I always get this backwards. The cycles which are permitted are exactly those in which the read-write edges are adjacent to one another. If they're non-adjacent, they should be prohibited. Am I doing this backwards? I'm sorry. I have to look this up every time.
No, this.
Blub, blub, blub.
I think this is also instilling confidence in all of the readers that even the greatest among us still don't have to look things up. I think that's good.
It's very hot here, and I'm losing focus.
That's true. For all of those who are listening, Kyle has graciously decided to phone in directly from a construction zone, at least as he refers to it. So there is no air.
There's no AC. I have all the windows open because I'm trying to vent out the ridiculous fumes from the finishing project I'm doing on the kitchen counter.
Oh, you didn't mention the fumes. Okay. Well, now
Those
we
might
have
also
to add a
be
disclaimer
interfering
at the
by
beginning of the show. Okay. Fine.
That's it. Blame it on the fumes.
Yeah. Like we were saying, G-non-adjacent, of course.
Right. So G-non-adjacent is important because snapshot isolation prevents it. You should never see a cycle in which the read-write dependency edges are not adjacent to each other in that cycle. Can I give you a concrete intuition for this?
Yeah. I mean, I'm really smart and I got it, but definitely for my kids that are upstairs, let's do it.
This is why it's one of my favorites, because it's so hard to wrap my head around. Like, snapshot isolation is this really clear definition. If you go look at Berenson et al. 1995, the Berenson couple and their colleagues at Microsoft Research and a few other places put together this paper that characterizes a database isolation scheme. And it's like, great, you want to do a transaction, you take a snapshot, nobody else gets to alter it, you do your transaction in that snapshot, and you put all of your writes back at some later time. When you commit, you can do that only if nobody else wrote the same items you wrote. That's it. Great. Simple, easy to understand, really intuitive, but it turns out that the safety property that generates is this weird G-non-adjacent thing. What on earth does that mean? Why? I would love to get a good intuition for why that is and somehow explain it to myself and others.
Well, the good news is I do believe there is a feedback form on the glossary that we are going to include. So the sum total of the internet will be made aware, and as long as we've confidently made the wrong statement, I'm sure we'll get the right one somewhere.
Yeah.
Isn't that one of those laws of the internet? I can't remember. So the favorite is G-non-adjacent, and I think one of the key properties is being able to explain it. Is that right?
Yeah, I have no idea how to explain this thing. I find it all the time. It's easy to detect. I can point to it and say this is bad, but I don't know how to intuitively capture that idea in total.
Man, distributed systems are wild. Is that part of what you think has drawn you to the discipline over time? Because there's all this, it's almost a study of edge cases, right? And in cases where we get to formalize, we see them enough, we can formalize them a little bit. But tomorrow is another day, even if it ends in Y, and who knows what's going to happen then.
Yeah, it's an endlessly challenging field. I could probably devote my whole life just to systems testing and not even scratch the surface. Every time I go to a conference, I have come back with this like list of papers people have told me about that I really want to read, or like concepts to understand, or software to test. I want to try FISB. I want to try P. I want to look at this new Z3 prover thing for transaction safety. And I don't have time for any of it. I am scrambling as hard as I can just to try and keep up with my little tiny corner of the world. But
that's the unfortunate thing. I feel like we're all heading in that direction where this is just exploding in complexity and where we can move forward in whatever tiny little blip that we can. But hopefully we'll get a glimpse at all of it, which is why, it's such a good thing to have all this compiled together. So when would I want to turn to the glossary? If I was in charge of running a distributed system, if I was trying to investigate it, what's the good moment for me to think, maybe I should go look at the thing?
I would say this is going to be most useful for early practitioners. I think it might also be helpful for people who are going through like a distributed systems class. I know that some folks refer to Jepsen's existing consistency model documentation in their educational work. But if I were an engineer, given the new system, I was asked to work on a database or to use a database, I'm hoping that this would be really directly helpful. Like, here's the kinds of faults I have to think about. I need to worry about crashes. I knew about that one, but I wasn't so much thinking about asymmetric network partitions, or I wasn't thinking about clock skew with this kind of scale. So
almost as a form of checklist of, hey, we don't necessarily have to guard against every fault type that could possibly exist, but we want to know of the things we like and the things we don't like, what are we going to put guardrails for?
Yeah, yeah. And I'm thinking that if you are a systems tester and you're asked to evaluate the safety of some system, you can kind of work through this. And the different sections will be useful at different parts. Like the consistency models checklist will be useful when you're trying to figure out what invariant am I even measuring about the system. Do I want snapshot isolation? Does it promise serializability? I want to try and formalize those vague claims that the system documentation has made into something testable. And then when I'm thinking about doing fault injection, obviously I'll go to the faults model and think like, okay, which of these faults seem legal and should be tested in our system? And which ones can we say, oh, if that happens, all bets are off?
What are good faults to let the dice roll as they may and say all bets are off?
Well, Byzantine faults, for example, lots of systems are not Byzantine fault tolerant, and that's okay in many contexts. Most of the time in a single data center where the software is run by a central entity of some kind, deployed by the same company or by the same people, your nodes are all going to be running the same software. They're probably not adversarial with each respect to each other. And so they're not going to be failing in the sorts of way that Byzantine fault-tolerant algorithms need to defend against. They might have accidental faults, which would fall under the distributed systems category of Byzantine, but they might be the kind that you can catch with like a checksum as opposed to having to do robust cryptographic verification of everybody else.
That makes sense because this all comes in layers, right? So we talk about this with people who are looking into the Antithesis platform, and one of the things that sometimes is on their mind is we deploy on AWS. How do we mock or otherwise do this appropriately inside of the Antithesis platform? And do we have to start digging into the verification of those mocks? And it's a question of scope. It's a question of where do you want to put the effort and where do you want to draw essentially a responsibility line. So we're trying to verify the correctness of a system. We're not trying to verify the correctness of a mock that is to the side of the system. Mm-hmm. And we can draw those lines, but first we have to draw with intention what those lines should be, right?
I also think the mock should generate behavior within the fault model or within the safety model. So if, for example, you're testing with S3, let us pretend, I believe S3 now offers linearizability, but let's say it didn't. Let's say it was eventually consistent. It might be possible that the mock software you deploy happens to be immediately consistent, and as a result, the test never observes a bug. But maybe a bug would exist if the mock were to occasionally return stale values. That's something which is not a fault, it's normal behavior for the system in question. But if the mock doesn't do it, you might not discover it experimentally.
Yep, that's very true. And it's something we run into, or at least it's something that we talk through with all of the customers that come on board, because you may want to test those, you may not. It's all a question of where you want to put the effort and the focus.
Yeah, one of the things that I did in Maelstrom, which is a little like a workbench for running toy distributed systems, is it actually gives you a few like mocks. It has, here's a linearizable key value store. And then it also has a version which is only sequentially consistent. And that version intentionally gives you stale reads and sometimes even allows you to like write to the past. It will reorder your writes if it can prove it was equivalent to a sequential history. And so it's deliberately adversarial in that sense. It's not Byzantine, but it's trying to expose you to all of the weird things that safety model would actually allow to make your systems testing more robust.
There's a question there of, I don't know enough about the mock literature in order to know whether this is commonly discussed, but essentially how adversarial you want your mocks to be is a sliding scale that you probably want to be able to flag or turn up or turn down as need be.
Yeah,
right?
And if it were, like there's a version of a mock just for availability testing where like it just returns error every time. Obviously that's not going to be very helpful. And in fact, even returning error for 1 in 3 or 4 requests might cause the system to be so slow that it misses a window of concurrency that would reveal some other bug. So some of the time you want everything to work fast, and some of the time you want everything to work really slow. And I imagine that that's part of why Antithesis being able to see like the entropy space is exploring is important.
It is, but there is a factor of judgment.
Yeah, of course.
So, the internal team here that was building the new database, was we call these brown M&Ms, right? Where we're intentionally injecting errors into different components of the system so that we can verify that we're exploring the correct space, and also so that we can verify the behavior of the system when it encounters those types of things. But how many M&Ms should be brown is a real question. And 1 out of 3 or 4 is a lot, Kyle. Like, it turns out not much can withstand that level of errors. So
yeah. There's a short world versus long world hypothesis to model checking, right?
Yeah.
And if you never get the long trace, maybe you never get to the interesting part of the system.
Exactly. And so we found experimentally with some of the things that we were doing, it was closer to 1 in 10,000 was a reasonable number. Now, this was for a high transactional system, so your mileage may vary in terms of what your requests per second and such are, but you might want to start with less because otherwise you will find that no progress will be made in the system if every other request fails in some fashion or another. But then you also get, I talk about it on a reasonable frequency, but my favorite error, that you get control over what kind of errors you get to do. So when I was working with one system, they were returning an XML fragment incorrectly, so it was an incorrect int file with an API, and so I had to bounce through a bunch of teams to get it fixed. And the way that they did the fix was they just wrapped that same fragment, string escaped, inside of a new XML document, which was not the behavior I wanted. But with a mock, you can choose to have that kind of behavior if you want. You could just drop the ending curly bracket. You could do whatever that are not impossible, but things become in your control, and then you're limited by your creativity in terms of what you can bring forth.
I'm reminded of the Microsoft Active Directory password changing API, in which, if I recall, this is 20 years ago, you have to take the string, put you base 64 encode it, and then you put literal quotes around it, then you base 64 encode that, and then you shove it into an LDAP, length of the limited string, and then
awesome.
You're working through layers down to the lizard brain of the system.
Oh man, that is the good stuff. All right, well let's think a little bit about the future here. So Kyle, you've been involved in the space for a while. Are you optimistic about how well we're handling distributed systems? Do you think that the future is bright?
I am really enthusiastic about distributed systems engineering in general. And I think that the state of the art has advanced significantly. Systems are becoming better specified. I'm seeing more use of formal models. I'm seeing more reliance on proven algorithms. Fewer people are sort of YOLOing their consistency model.
That's not what I've seen the vibe coders do these days.
So the second part of that is, yes, there is this advent of using an automated bullshit generator to emit programs. And, corpus, text and image synthesis is really cool technology. But distributed systems tend to be characterized by really subtle bugs that require building a strong model in your head of correctness, or some sort of really sophisticated formal verification, which, while it's been done occasionally, maybe hasn't panned out as broadly as we'd hope. I don't often see a TLA specification which is always updated and is reflective of and machine-checked equivalents to the actual implementation of the system.
Why do you think that is?
TLA is sort of exhausting. I love this technology, but I'm not very good at it myself. It also requires investing in something which isn't really a feature, and I think that there can be managerial pressure to just deliver, performance and bug fixes, and not to worry so much about maintaining the specification. And as you evolve the system, it's easy to diverge from the spec. And there's a tooling weakness in that, showing the equivalence of this string of REST code to this TLA model is sort of an open problem. Sometimes you can do what's called extraction, where you take like a cock-proven algorithm or a TLA-proven system, and you extract some code into the system. But then once you've done that, it's kind of a one-way thing or a one-time process. You can't like continually re-extract and merge with the new system with all of its optimizations and different bells and whistles. And so I'm not surprised that those things tend to diverge over time.
Because it's like documentation, but with more thought work.
Yeah, I mean, documentation can be held up by a human next to the code itself and compared, and people can do that process. But it would be hard to machine check documentation. In theory, TLA is a formal specification, and in theory, a language like, well, I guess not C, but many languages are reasonably specified, and you should be able to maybe prove some properties about the isomorphism between the two formal languages. This is, as I understand it, an active area of research, but this is not my specialty, so I probably can't speak too much on it.
It's fair. We're asking you to go out a little bit on a limb here, and that's okay.
But I do worry about the vibe coding thing. Because like the systems bugs at the level that I find them, the system doesn't give you an obvious error or stack trace. It's like, great, you executed this history of 5,000 transactions, and these 4 of them had this weird dependency cycle, which arose because of the implicit dance of locks and message passing and all the stuff that happened across machines. And to trace and debug that, you need to have a really good mental model and the ability to synthesize information about multiple levels of the system, all the way from like the hardware to the the kernel TCP stack to the application, and maybe even the way that the user's semantics of the transaction are meant to be interpreted. LLMs make it really easy to emit large volumes of code. They don't make it easy for you to build that mental model about the code that you emitted. And if anything, it may make it harder by emitting subtle bugs that look very correct on the surface, but conceal some, error. I suspect, and this is not a rigorous analysis, but just kind of based on the systems that I have tested, which were generated in part by large language models, that my job would be very secure for some time.
It's actually a very interesting problem space I hear you highlight, which is usually we talk a lot about intention onto the screen, whether that's direct typing the code or trying to convey intention to an LLM in some fashion to create the code and all of the imprecision that's involved there. But you're almost arguing the other way of, even if we could slurp the entirety of, let's say, every machine state and like the complete memory complex and everything into an LLM somehow, like conveying it back to us in a way that is understandable and has a reasonable comprehension of what the mental model and such would be, is way off the radar of where we are now and poses a real gap for where we might see improvement in that kind of space, right? Because
both directions matter. I think you're right to call up the opposite way, that specifying the system in the first place is often really hard to do. And many times when I come in to help a vendor test something, they don't quite know what it's supposed to do. Part of a Jepsen report is often like deciding what is it that we actually claim, what sort of things should be safe. So yes, you're right. Like specifying that thing in plain English is really challenging. And even if you could specify it perfectly, using a system which will make some stochastic errors, that's just in the nature of stochastic generation, and which produces, because of the way it's trained, produces plausible programs, things that look right to humans. I think it's likely that it's more difficult to analyze an LLM's output, to read it and catch the bugs it's making, than it would be to maybe write the code yourself and to build that model in your head. I find it much harder to debug other people's code than my own, and to do it from a stochastically generated code that doesn't necessarily make the same classes of mistakes, or that might, choose misleading variable names, because that thing appears commonly in the corpus. For whatever inscrutable
I find it
reason.
much harder to debug my own code because I'm terrible. Like that's the easy answer for what's going on.
Even debugging my own code from like 10 years ago is really difficult. Yeah, I have to. There's a process, I think, at least for my debugging, where I like sink my brain into the problem space, and a part of that is like kind of rereading or retyping like parts of the code just to build up that mental scaffolding again for like, why does this thing work? And I
For
keep in mind,
sure.
Zach Tellman has a really good thing on this in, I think, his second book on programming theory, that like, every model is inaccurate in some way and necessarily fails to capture some nuance or some meaning. And when we write programs which are correct, we are deciding what correctness counts for, and we are eliding lots of other things, lots of other details. And that process of eliding, of choosing the right context, I care about the return value, but I don't care about the time it took. Or maybe I do for security reasons. Those sorts of subtleties don't necessarily show up in the code. They're things that get built up in your mental model for something.
Or are practically felt in some sense, using whatever intuitive sense we in all
Yeah,
the
James C.
baked-in
Scott
stuff
would
we've
call it
got.
this, I think I'm going to butcher the pronunciation, but metis, the sort of like the knack, the technical know-how that comes from doing something in depth in 1,000 different ways in different contexts. You build up this deep intuitive understanding. I can ride a bicycle down a street in a city I've never been in before because I have built up so many experiences of riding bicycles in different streets before. That's not a proven theory of bicycle riding. That is an ongoing, elaborated mental process.
Or it's just a continuous unit test check to see if you can still ride a bicycle or not.
Well, yes,
And
if I had
eventually
time
you might
travel
fail.
debugging, I could simply crash as often as I liked. I would intentionally drive into traffic and then rewind my state.
Wouldn't that solve so many problems? Just a quick rewind, just like in Braid? Oh man, I got to stop with the video game references today. So you've obviously worked on a lot of systems. What has been one of the most surprising things that you've seen about a system that you've worked on, good or bad? Either, wow, this was quite a stumble, or wow, this was quite a surprise in a good way.
Yeah, I want to call out Datomic here. Datomic's team has built this sort of like alien database in a sense. It's obviously drawing on a long history of existing thought, but it has a really beautiful way of interacting with it. You get a variable which is a handle to the entire database state, and it's just this little tiny thing which you could even pass across the network if you wanted to. And that handle, you can ask any number of queries in your code, and they all happen at the same moment in time on this read-only view of the database. That notion of making now an explicit thing, something which you could share across processes, I think is really powerful. I'd love to see more databases doing that.
Datomic, of course, being the closure-based database that has a lot of very interesting properties. And they don't even use SQL, right? They use...
Yeah, there's a data log style API where you can write sort of unification queries. I'm looking for a person who has a name, and I'm looking also for a name which is the same name as the person's name, which also appears in a list of people who have cats. And I'd also like to know about a cat who happens to have the same person who shows up in that list. It will unify those things, generate a query plan, and then find you all the cats and all the people who correspond to them. It's a totally different way of looking at it, but of course, Datalog and SQL are in some sense sort of both declarative visions of the same idea.
Squint really hard. You could almost see where they're both
Yeah,
coming from.
if you like rotate at right angles to reality, this is like a query engine. And the Datalog and Prolog people have like known this for years. Logic programming is really cool stuff. And it's often, I think, a more natural way to phrase things. I struggle with more complex SQL queries. But the most surprising thing for me about Datomic was actually the transaction model, which does this really unusual thing. Transactions are serializable in the sense that every transaction executes as an atomic unit, and they appear to execute in some total order. Fantastic. That's easy to reason about. But inside of a transaction, there are these things called transaction functions, which can read the current state of the database and produce new facts you'd like to add. And all of those transaction functions run logically concurrently. They all take the same input state and they produce new facts, and those facts are merged. They don't see each other, which means that they don't compose in the same way that transactions do. Transactions stack one on top of the next. If you prove an invariant is preserved by one transaction, if you prove invariants are preserved by each transaction separately, any serializable history must also preserve that same invariant. That's like a key advantage of serializability. But transaction functions, if you prove a property is locally true of any transaction function, compositions of those functions, calling multiple ones in the same transaction, may actually be unsafe in a way that they are not in almost every other database. And this is just a totally, bespoke, different vision of the way that like change and temporality should be viewed in the database. And Atomic feels strongly this is their sort of philosophical right to claim this, that in this ontology there is no time inside a transaction. Why would you even want that? And yeah, okay, I guess I can get behind that. But it was deeply confusing to me as somebody who is used to this sequential model of thinking, even in Clojure.
Yeah, I seem to remember that the big update that came out of that report on their side was to just bold a section of their documentation to be clear about this.
Yeah, because the docs said it. And like I read those docs carefully and I got this wrong. Because there were other parts of the docs that said like, I think it was like transaction functions execute atomically in sequence or something like that. And it made it look as if they were supposed to do invariants, but they're really not.
Interesting. Okay. So when you're working with someone new, can I ask you a little bit, Kyle, about how do you feel working with a new customer? Is there a sense of excitement, of curiosity?
Oh, yeah.
Do you have a sense of ego and you feel a little bit of that pressure of like, boy, I've found a lot of cool stuff in the past. I don't know if we're going to do it today. Or how does it feel working with someone new?
I think there's sort of two big emotions that drive my work, and one of them is like a sort of Lutheran sense of duty, like, oh gosh, I have to work really hard and like make things good for this customer.
Yeah.
And there is that fear, like, yes, I've found bugs in almost every database I've tested. Datomic is one of the few that basically we didn't find anything. But it could always happen again, and oh gosh, what happens if I put in all this work and I don't find anything like helpful for them? In some sense, that's a success because it says they did their engineering work well, and it validates that work externally, which is good for marketing. But in another sense, I'm asking
confidence.
myself, yeah. But did I do my job well? If I didn't find a bug, or the test's too weak? So that's definitely one factor.
It reminds me of Will Wilson, CEO of Antithesis, gave a talk a long time ago at Strange Loop. And one of the questions that was asked, because he was talking about the deterministic simulation testing framework for FoundationDB. And one of the questions he was asked in the Q&A kind of haunts my brain a little bit, because he was asked, does anything worry you? Something along these lines. I'm going to mangle the quote here, but he's going to say, does anything worry about taking this approach to doing testing? And I think he said, when we talk amongst ourselves, the thing that worries us most is that all we are doing is training the engineers to write bugs that we can't find with this approach. Almost
Yes,
like an evolutionary approach, right? The bugs are evolving and they are getting resistant to all of our techniques.
And that absolutely can happen. I have the same problem. Sometimes I will report a bug in a system, and the response is, oh, let's add a timeout. And the timeout makes it so that I can't reproduce the bug anymore, because it just pushes the concurrent section like away. But of course, if the timeout weren't reliable, or if the network were to delay things in just the right way, you could get there again. So the problem isn't gone, it's just less likely. I don't know how to solve that. Besides like urging people to kind of eat their vegetables and think about logical correctness instead of just using timing tricks.
Yes. Well, I think about it back to what you said earlier, which is that it's important to understand what we want our systems to do. And in the world where, let's just say, code generation that is mid, perhaps, becomes more and more frequent. As I'll put it this way, as more and more code is generated, which creates more and more of a surface for potential issues to arise, being clearer about our intention at any scope and any level, in any fidelity that can be cycled back and forth seems of increasing importance, because without it, we are looking for behaviors and systems where we don't know quite what they want, and we can't tell when we come into a problem unless it starts with a 500 or, ends in a non-zero exit code that is like, oh no, that was probably not bad. And then the Erlang people are going to yell and be like, no, it's fine. But in general, we should probably get better at specifying what our intent is of the systems that we build, both at the technical level and at the business level, right? Because it is good to build a serializable system. It is less good if we don't understand how that connects to the people we're trying to serve in a larger sense. So I am looking forward to the evolution of the field, connecting the dots on those previously, because I have a great faith in the development community being able to create very practical frameworks for things that sometimes get bogged down in academia a lot, right? Like there are a lot of systems that have emerged in industry that are really cool and never came out of an academic paper, right? The vice versa is also true. Like there's been some really cool implementations of academic stuff, but I love that grit that comes from the wider field of engineering. And if they have to turn their eye towards this intentional correctness problem, I'm looking forward to what comes out of that. I think that's an exciting time. It's reflecting the question back on myself of what are you looking forward to in distributed systems? I believe in the adaptability of us to solve this problem.
And maybe we throw more stochastic methods at the problem. There was the Amazon piece that came out a few weeks ago about extracting a specification from a system using a large language model and then asking it to, go back and find bugs. And if I recall, they did surface some sort of error in the system that way.
And I'm sure today is the worst. It's the worst it'll ever be today, assuming continued up and to the right, because number always go up. I've never seen number go down as far as I'm aware of. But there's going to be interesting stuff ahead, and I'm looking forward to it. Kyle, what I want to end here, because first of all, thank you for the time. It's been a longer conversation. I really appreciate it. Is there anything else that you would like to share with the audience before you go?
I am really frustrated by the lack of reproducibility in Jepsen. I find a bug and I can't tell people how to get it reliably. I can say if you run this for 5 minutes, it will likely show up, or maybe it takes 6 hours, and there is no good answer for that. Antithesis is theoretically the thing I want, and if I can figure out how to make Jepsen fit well inside of that, I would be very excited.
I'm sure I'm going to put this straight to the team and see what they can think about it for sure. Well, that's a great thought to end on. There are always things that we could improve, right?
Yeah. Oh, I have a bunch of work to do in Jepsen just for reproducibility's sake. Part of working with Antithesis has been realizing all the places in Jepsen where I have uncontrolled non-determinism or I/O that now makes it really hard for me to have some other system drive the entropy of the test.
Yes. We're all trying to do the right thing. We're all trying to move in the right direction. And maybe one day we'll get all the bugs, right? Maybe, Kyle?
Every single one of them.
Love it. Well, with that, I think we will sign off here tonight. Thank you, everyone, for listening, and I hope you have a good day. Thanks for checking out the Bug Bash podcast. If you want to reach out, maybe with an idea for the show, or maybe you want to be on it, send us an email at bugbash@antithesis.com. Or, if chat's more your style, head over to antithesis.com and scroll to the bottom, where you'll find the link to our Discord. Until next time.